So today we'll be learning about the interesting hypothesis, that's lattice hypothesis. Lattice hypothesis explains about the antigen and antibody reaction that is simply applied to precipitation and agglutination reactions, and most of the common tests you'll be knowing by next classes. So there are several experiments, but based upon this hypothesis. How is it? So in the last class I told you, if you have not seen the last class, please go to there and qualitative quantitative test, why it is better and not better. I will give it in the I button. But from the quantitative test, we came to know that is better, quantitative is better. But why it is better? This explains the hypothesis. So here, a sera containing antibodies serially diluted in this experiment and then reacted with known concentration of the antigen. Okay? So the patient's serum, you have taken the patient's serum, it has been serially diluted, whatever concentration, maybe 1 nanomole, 2 nanomole, 3 nanomole, whatever it is. And then a known concentration of antigen is given with all the wells or all the tubes and then reacted and incubated. So 3 tubes, if you take 3 tubes, here it is tube 1, tube 2 and tube 3. So what will happen? Because it is diluted, right? So from higher antibody concentration to lower antibody concentration, the dilution will be there. So what will be the result of the experiment? The lattice hypothesis says that if you give excess antibody compared to the antigen, so this is antibody and these red ones are the antigens. So if you give more antibody compared to the antigen, there will be no observable reaction that I told in quantitative test. Please observe the video or see the video. So because all the antibodies are not occupied with all the antigens. First case. Second case, there is no such interaction between the antibodies and the antigens which may form a structure that may be observable. So this excess antibody case, he gave a name, that is Prozone effect. So if you give more antibody than the antigen, it will give you a Prozone effect which will not be observable in experiment where antigen and antibody are directly given for a reaction. Let's see the tube 2. Here you see an interesting structure formed due to equal amount of antigen and antibody. So a multivalent antigen is bound by bivalent antibodies where the equal concentration of antigen and antibody are there. So it will give you a zone of equivalence. This zone of equivalence give you the lattice structure. This is the lattice structure. Now this structure is observable. So if you give an antigen antibody reaction in a tube or in a gel or a semi-solid medium, whatever it is, you will be observing this structure if it is formed there. So lattice formation is mandatory, either it is a solution or in a gel format. This lattice is observable. By observing this lattice, you can say the test is positive or negative. If it is there, it is positive. If it is not there, it is negative. In a qualitative test, you will be interpreting the result like this. Now, in the third case, tube 3, excess antigens are there comparing to antibodies. So here all the antibodies are occupied with the antigen, right? Just opposite to the first tube. But why there is no lattice formation? Because the antigens, the excess of antigens will interfere with the electrostatic interactions or the weak interactions that are forming with the antigen antibody, which help to maintain the lattice structure. The antigen, excess of antigen will interfere with the antigens already bound to the antibodies, and that will inhibit the formation of the lattice structure. It will give you a post-zone effect. Post-zone effect. So first one, in case of antibody access, it will give you a Prozone effect. If it is equal, it will give you a zone of equivalence or lattice structure, lattice formation state. And if it is antigen is excess than the antibody, then it will give you a post-zone effect. So there will be no observable reaction that can be interpreted as positive. So if the patient contains this amount of antibody, you will be interpreting the patient as negative, because you are not able to see any kind of structure or any kind of band which is visually you can mark or measure through your eye. In the first case also, you will interpret the result as the patient is negative, but actually there is a antibody present. Even in this case, it is more than expected, and in that case it is lesser than expected but above the cutoff range. So in that both the cases the patient is positive, but your qualitative test or qualitative immunoassay will give you a false negative result, whereas in this structure in the qualitative test will give positive visualization which will be interpreted as positive patient. So that problem is solution given by the quantitative assays. Quantitative assays will not measure any kind of visual structure. It will directly measure the concentration of the antigen or the antibody above the cutoff level. So if it is above the cutoff level, means the patient is positive. And also you will be able to determine the exact concentration of the antibody there or the antigen there. So antibody or antigen titer both can be measured. So this lattice hypothesis gives you a unique idea why antigen antibody must be equal to be interpreted as positive result in a SERA. So I hope this is clear, and this is linked with the qualitative and quantitative assays regarding precipitation and agglutination reactions or the test medically very relevant. So please go through that video and compare it with this. So you will be understanding why quantitative is much more better than qualitative. Lattice hypothesis gives you the explanation. So I hope you have understood the concept. If my classes are really helping you in your studies and it is really clearing your concept, so give a big thumbs up and don't forget to subscribe my channel Bio Affairs. This type of subscription and likes give me the enthusiasm to prepare more futuristic classes for you guys, to make your classes more conceptual